This is just a short video in response to the question asked about the broken wave calculator or using Java, the wave calculator. Java is a mess, but certainly can get it to work. But there are alternatives to calculating that relation. So one thing, so what we're looking at is this idea of wave dispersion. So what the calculator does, see if we can find the equation here. Dispersion, ocean, wavelength. So I'm going to search Google about the wiki page. Okay. Here it is. Okay. So what we discussed in class about water waves is that there's a general dispersion relation which relates the period t and the wavelength lambda. You can see that in this green box here, written in two different forms. So this forms the dimensions in this form are probably a little more familiar to people. We have lambda, the wavelength, t, the period. And you can see it's a nonlinear equation. It's an implicit equation in the sense if you have period and you'd like to know in depth, and you'd like to know what the wavelength is associated with that, then you have to solve this implicit relation. So you can't solve directly for lambda. Now there are techniques to doing that. A great example of that is Newton's method, which the person who asked the question may or may not be aware of. But let's see, in the online calculator, that's essentially what it does, is it solves this implicit equation. Let's just see, I'm going to try this Wolfram alpha calculator. So this is an online resource. I don't use it much. You end up having to pay for some things, but it's worth a try. So for example, if you want to solve an equation, you say solve 2 times x minus 2 equals 0, right? So what's the solution of that equation? It's x equals 1. Let's see if Wolfram can solve it. Return. Okay, solve x equals 1. So this is an equation for a line. Basically looking for the solution to this equation, which is what we call the root, the position at which x, the x for which this equation is true. The x occurs here, x equals 1. Of course, this is a simple linear algebraic equation, which you were probably first introduced to if you are in the US in, I don't know, 8th or 9th grade, something like that, and probably much earlier if you were not from the US. So we have x equals 1. Now let's go, maybe I can stay on this page here. Now if you consider a nonlinear equation, how about sine x, solve sine x equals 0. What are the solutions of this equation? And I say solutions because there's more than one. We know sine of 0 is 0. We know sine of pi is 0. We know sine of 2 pi is 0. And then we know sine of 3 pi is 0, etc. So there's many solutions or roots to this equation. I'm just going to hit return. Hopefully this will... Okay, so what did Wolfram do? It found me some solutions plotted here. X equals 0, x equals pi, x equals minus pi, and it says here the general solution is x equals pi n in the set of real numbers. So we have pi times 1, pi times 2, pi times 3, pi times 4. So there's an infinite number of solutions to this equation. Now what about our general dispersion equation? So I'm going to go back to my wiki page. Here's the equation. What I'm going to do, and I don't know if this is necessary in Wolfram or not, but it's generally the approach that I have because I use Newton's method for solving these kind of things. I'm going to pull lambda onto this side of the equation. So I'm going to say this part minus lambda equals 0. So I'm just pulling lambda over to the same side. So I have g over 2 pi times t squared. I have to go back and forth between these two tabs. So I'm going to say solve g over 2 times pi. So I could pre-calculate that as some kind of constant. Actually, Wolfram has no idea. I might know what pi is, but I'm going to assume it doesn't. And doesn't know what g is probably. So I'm going to write those explicitly with approximately the numbers to 2 digits times t squared. I don't know. For a wave, let's just do a period of 10 seconds, and we'll do a depth. What are we going to make for a depth? How about 1,000 meters? So I'll say 10 times 10. That's 10 squared. Here, the period squared. then hyperbolic tangent of 2 pi h over lambda. So let me come back here, times the hyperbolic tangent, which I'll assume is tan h in Wolfram, 2 times roughly pi again, times the depth, which I'm going to say is 1,000 meters, divided by lambda. Now I don't know if I have to call my unknown variable x or not. I'm going to call it x. Well, let's just see if lambda works. Minus lambda, remember I brought lambda over to the same side, equals 0. So that's the equation I'm solving. So again, this equation where t is known, 10, h is known, 1,000, the only unknown in this thing is lambda. But I can't get this lambda outside the tan h. That's essentially the issue. There's a lambda here, there's a lambda here, and I want to know what lambda satisfies excuse me, this equality. So I brought lambda to this side, so I have this thing minus lambda equals 0. I'm trying to find the lambda that satisfies that. There may be more than one. I suspect there'll be one, and, well, there might be another one, but let's see. Let me just double check this. 9.8 over 2 times pi times 10 times 10 tan h. Looks okay to me. Let's see what Wolfram has for me here. Okay, so it came up with a solution. There's some options to this solution. More digits. I don't really want more digits, so this is fine. Now, I see it's written it out a little bit better here. Actually, you can see it more explicitly. 9.1 over 2 times pi. And I put the 2 times pi in parentheses so it executes that in the denominator here. But I could pre-compute this whole constant and then stick it here. Times 10 times 10 tan h 2 pi, that's h over lambda minus lambda equals 0, and it comes up with a lambda of 156.21. Now let me just open a terminal here, and I'm just going to write that here so I have it. Alright, so 156.21 was the wavelength. This is from the general dispersion relationship. Now I'm kind of assuming, well, what this implies to me is that this is a deep water wave because we have 1,000 meters of water, 156 meter wavelength. So that means if I cut this tan h off here, so remember in the limit where in this limit of tan h approaches 1, if our lambda is small relative to 1,000, or the deep water limit. So as we move to the deep water limit, we had a different dispersion relation which looks something like this. Basically the tan h is gone, and it approaches asymptotes toward 1. I'm going to resolve this equation without it and see how close it is. So I cut the tan h, I'm going to hit return again, or enter, and I get this. This is not a helpful number, I have to be honest. If I was looking about the right name, oh, maybe I got to hit this button. Oh, yeah, that worked. Okay, so I get, it's the exact same number, 156.21. So this is such a deep water wave that I can just use effectively that deep water wave limit for the parameters that I happen to put in here, which may or may not have anything to do with the exam. I was just making them up off the cuff. So this is just an example of using, if you have these kind of equations you have to solve rather than going to the calculators, which program, basically what we're doing here is pre-programmed, but Wolfram allows you, and other resources if you're comfortable with MATLAB and other computing things, but this tool I find interesting. This is only the second time I've used it, but it looks like it's a good resource for students who have to solve, not complex systems, but systems for which they can't take down a pencil and paper and do it, but where they're not at the comfort level of going to something like Python to do it. This seems to be a nice route. So that's about it. So the point of this example was you can solve the dispersion equation. I'm not sure this was necessary to solve the test problem or not, but this gives you an example of bypassing the calculator. Of course, once you have lambda and t, you can get at the wave speed pretty easily, and that's the other thing that the Delaware calculator calculates for you, if that's a quantity of interest. So that's all.